sure that this can connect to everything. Okay, I think I'm sharing my slides now.
There we go. Yes. Do you want to advance just to make sure?
Sure. Great. All right.
I didn't see it. Can you advance the slide just to make
Sorry.
sure?
Yeah.
Okay, great. All right. Well, welcome back. We are on pitch number 2 for day 3 of Innovation Week at Rensselaer in the Capital Region. Today we have Dr. Joseph Borrello, who's coming to us from Mount Sinai Biodesign Program in New York City. And we're happy to have him today because he's going to talk to us about some metamechanical materials. So we're interested in to see how we're going to be able to build out your team on both the business and on the design side of this project. So I will hand it off to you.
Awesome. Thank you so much. And I think I'm probably the most newly minted PhD who's going to be presenting today. This is based off of work that I actually did my PhD dissertation on, which just concluded in July. So very exciting. But what we found over the course of that work is it really spawned a whole lot of new areas of investigation, and that's what I'm going to be talking about today in this quick presentation. And so my thesis and kind of the underlying philosophy of this project and all the related projects is that medical implants are very good at solving problems in the short term, but actually have a lot of problems in the long term. And so 20% of all adults in the US have a medical implant of some kind. And 10% of those implants will fail and need to be removed for no other reason than because they don't mechanically integrate appropriately with the surrounding tissue in the body. So this leads to over $10 billion annually in revision surgery costs and removal surgery costs, and basically people needing to go back into the OR to solve a problem that was supposed to be solved when the implant was placed initially. And so what we really envision is the next generation of these medical implants. And now my slides are frozen, but can you guys still, am I frozen?
No, your audio is fine.
Yeah. Okay, my audio is fine, so at least I'll be able to give this without that. But okay, they're here now. The next generation medical implants is not going to be just kind of the solid pieces of titanium or meshes of PTFE that we've used in the past, but it's really going to leverage our newfound computational and fabrication technologies to combine materials and designs in unique and more biomimetic ways. And so the category of materials that my research is focused on is mechanical metamaterials. And this is a class of This is a class of materials that have unique mechanical properties, not from the material they're comprised of, but from the structure they possess. And so I don't know how well these GIFs are playing for you guys on the other end, but you can get some very unexpected behaviors from mechanical metamaterials through taking a conventional material and just designing it in a unique way. And so you can take instances like the structure on the right that translates a downward push or pull into a rotational motion. You can prescribe unique ways for a structure to crumple and fail so that you concentrate forces in one location and not another. And you can even prescribe materials that get thicker when you stretch them instead of thinner. And so that class of materials specifically is called auxetics. And they are unique in the sense that they get thicker when you stretch them instead of thinner. And so if you think about a rubber band and how a rubber band behaves when you stretch on it, it gets longer, you pull on it, but the middle of the rubber band actually gets thinner. Auxetic materials work differently. They, through their structure, actually get thicker when you stretch them instead of thinner. And so this is a very kind of unusual property. It's something that my PhD thesis sought to exploit for use in heart tissue. And really the phenomenon arises, like I mentioned, because of the unique structures that these materials are made out of at the kind of the microscopic scale. So the thesis work focused on making a auxetic mechanical metamaterial patch that you would put onto the heart following a heart attack. When you lose non-beating tissue, basically the scar can no longer beat, and so it can't contribute to pumping blood throughout the body. And our rationale was, can we put a material over that scar that is structured in such a way that it behaves like healthy heart tissue? When the heart beats, it gets thicker along with the rest of the healthy portions of the heart, and that's what we sought to use auxetic materials for. But there's a lot of need beyond the heart, and actually, from a commercial perspective, especially, a lot more pressing needs, and from a clinical perspective, the heart case is very interesting, and it's an interesting scientific question, but there aren't really many clinical instances of people needing a procedure like we propose these days, because we've just gotten very good at other interventions. Where there is a lot of need still is in peripheral vascular grafts. So another part of the cardiovascular system with some of the same considerations, but really a different form factor and a different surgical approach. And so specifically peripheral vasculature, kind of the vessels in your arms and your legs. As you move away from the heart, everything thins out. Your vessels become smaller and more fine to reach more remote parts of the body, but that also makes them more prone to getting blocked with advanced age or conditions like diabetes. And so in some cases, when a artery is blocked in your legs or in your arms, it requires the placement of a graft to basically bypass that that region that's become blocked up. And so usually these grafts, when possible, are made from tissue inside your body. They try to harvest vessels from other regions of your leg or your arm to use for this grafting material. But in a lot of cases, when a patient is chronically ill with a condition like diabetes, you need to use something synthetic like this PTFE tube, which is basically a tube of Teflon that you suture on in this bypass graft structure. And so that's really good at not getting clotted the way the blocked vessel did. But what happens is, because PTFE doesn't have the same mechanical properties as native blood vessel, you do get a clot formation and actual cell buildup at the interface between the Teflon tube and the blood vessel. And so this blockage, this reduction of flow is called a reduction in patency, which is just that less blood moves through the system than it's intended to. And so you end up with another situation of needing to go back in and do revision surgeries or swap out vasculature after so many years, swap out grafts after so many years, and you end up with, in the long term, something that doesn't actually solve your problem. And so the prompt here is really, can we take the things we learned from the heart? Can we take some of that core scientific understanding and technology, reapply it to blood vessels, and build a graft material that is either auxetic or some other kind of metamaterial structure? That's still very much an open question, but something that behaves more like the native tissue in the body, because there's a lot of consensus that you want to replace these vessel grafts with something as close to healthy blood vessel as possible. But in some cases, it's just not available from the body. And the stuff that's used clinically really isn't as close as it could be mechanically. And so the ask is really kind of threefold. There's design considerations that still need to be applied, prototyping, of course, and then customer discovery on the business front. And so there's a lot of ways you can tweak mechanical metamaterials. This is one example of just changing the angle of this structure. And you can get a lot of different mechanical responses. And so there's a lot of work to be done on the front of blood vessel mechanics and understanding what might be the best design to actually replicate the mechanical behavior of a blood vessel. And once you've solved that problem, how do you actually go and make the thing? There's a lot of different techniques that we have access to at Mount Sinai and at Mount Sinai Biodesign, and potentially beyond, relating to advanced manufacturing and other prototyping approaches that I think are of interest and we would be interested in exploring further. And then kind of simultaneous to those two things, really building out a deeper understanding of the clinical needs, what exactly a metamaterial vascular graft might look like when used in a clinical setting, and what a pathway would be to bring that to market. And so I think my little customer discovery graphic is still showing up, but that is the bulk of the presentation. I think if there's any questions, happy to answer them.
That was great, Joseph. Thank you so much. Now, can you share with us if you have done customer discovery to date?
On the vascular front, not much. We actually went through a regional ICOR program, looking at the heart application, and that was actually the first place where we even had the idea to apply this to blood vessels instead of to the heart, because that was the first place we heard from cardiovascular surgeons that it was an interesting problem to solve for heart attacks, but not actually a very urgent problem to solve for heart attacks, and that vessels were actually an area where there was more need for new graft materials. But we never really went very far beyond that in terms of digging down onto that space.
Okay, that's a great open door for a team to walk into and help with. Now, while you demonstrated there are multiple applications for your technology, they're all within the same field. So, can you share with us a couple examples of the stakeholders that are involved? That are involved in the ecosystem that you've been diving into?
Sure. So I think naturally there's going to be cardiovascular surgeons as one stakeholder. They're the end user, I guess, one of the two end users of this of a technology like this. They need to be able to buy into the technology and be interested in using it in their practice, and that's always a process that I think is multifaceted. We see it a lot in other projects in biodesign as well. Patients are another group. They are usually they're receiving this. They don't necessarily get a say all the time in what this physician chooses for them. But I think keeping their needs in mind is important when talking to physicians and other stakeholders around the idea that this is it is like a driving factor. I think that physicians do want to do right by their patients, and so understanding what their patients would consider as doing right by them is a great way to kind of help convey value to a physician. Depending on the pathway it takes, I think there's also device companies down the line through partnerships or potential acquisitions, manufacturers. I think a whole host of things, but those are the ones that jump to mind right now.
Those are great. I just wanted to ask one question on the design side. Logistically, how would a biomedical engineer student be able to work with you on the design aspect? Will this require trips down to the city to get into the space working with you, or are there some remote possibilities?
I think the opportunity to come down to the city and work with us in biodesign is definitely on the table, but it's definitely not a requirement either, especially on the designing front versus the fabrication front. A lot of this work happens computationally to screen all the different design possibilities and compare them against the known biological mechanical parameters. And so a lot of that can happen remotely, can happen virtually. It's a lot of like computer modeling and simulation work, at least to begin with. And then I think we try to use an approach similar to the way some groups discover drugs now, which is you start with a big computational screen, identify a few candidates that you actually want to make in the lab, and then that would be the phase of coming down, fabricating, prototyping, and testing things on the bench.
Fantastic. We do have Majdi here. Majdi, do you have any questions for Dr. Barlow?
I think my only question would be in terms of manufacturing, since it's such a kind of diverse product line with the aesthetic metamaterials, do you see it being more expensive, or would you see a process in which the price of these materials would be similar and thus more appealing for people to utilize?
I think there's at least the possibility that it would be comparable in price. I think that partly depends on what the way to fabricate them ends up being. What we've experimented with for the heart patch was actually using the same kind of technology that other patch graft materials are made with, which is digital knitting and weaving technologies. And so in that case, ultimately you kind of get the same economy of scale and the same unit economics, and a patch like that would come out to be about the same price. Ideally, something similar is possible for vascular grafts, but I think it's the project is so early. It's really a concept at this point based on some stuff we learned somewhere else. It is still a bit of an unknown, and I think that's one of the things I'm curious in working with a team to find out more about.
That makes sense. I think because my specialty is in more business development and data analytics, so that could be really interesting to kind of go into and see how the operations and see, whether or not you could charge some sort of premium for a product that will last a lifetime versus what's on the market today.
Right. Awesome.
All right, well, this project is very fascinating, and I believe students are going to be definitely interested in working with you. So just as far as next steps, this recording will be posted so students can view it on demand, and they have until the 17th of October to select the project they'd like to work with. Within the week following, we will be getting a list of students to you so that you can review who's interested, and we will get that pair connected this calendar year so that you can get off to a running start come the spring semester in both courses.
Great.
Sound like a plan?
Yeah, that sounds awesome.
All right. Thanks so much for your time today.
Yeah, thanks so much for having me.
Okay.